Yeah, I'm going to talk to you about what we've been able to learn recently through using some routinely collected healthcare data from Oxfordshire. And there are 5 projects I'm going to talk you through. And the idea behind presenting them is, one, they've got some specific findings, which may be of interest to some of you, but also they're examples of approaches that have, I think, broader applications as well. So the 5 things I'm going to go through with you is to firstly ask the question, well, does antibiotic resistance matter in Oxfordshire? Or at least to ask the question, in a specific situation, does it matter? Then, maybe having established that actually you might want to use broad spectrum antibiotics in some instances where antibiotic resistance exists, do we always need to use them? Or are there actually instances where we're perhaps overusing antibiotics? We can also use this data to think about giving people the right amount of antibiotics, thinking about dosing them more appropriately. And then also to ask the question, well, what does a normal response to infection look like? So how do we know that treatment's working? And then the final piece, which is slightly different to the other 4, but is to think a little bit about how we can help patients get home quicker by understanding those who are likely to go home soon. And there's some sort of fundamental thing that's useful here, which is that actually there's quite a lot of variation in medical practice that just occurs through preferences, through differences in people's training, just through the circumstances of what's going on in the hospital. And so actually, this is quite a key enabler of several of the analyses, because it allows us to see what happens under different sort of treatment choices and treatment pathways. So the first thing, I know some of you know this very well, but just to make sure everyone is sort of up to speed, is just to talk a little bit about, in a minute or so, the sort of history of the electronic healthcare data that we have from Oxfordshire. So various people, so John Finney, David Wiley, Tim Peters, Sarah Walker there, about 15 years ago or so, put together some key bits of information to help us think more about infections in Oxfordshire. And what this was is information about who'd come to hospital, information on their blood test results, information on their microbiology results, and then frankly anything else they could find in a sort of magpie type way, trying to collect different data sources from across the hospital. And all of this was linked within the NHS and then de-identified and used to create what became the Infections in Oxfordshire Research Database. And this has successfully supported over 90 research studies to date, including sort of publications in high impact journals like the New England Journal of Medicine, the Lancet, and so on. So it's really been a very successful exercise. What's in it? So we have about 750,000 people who live in Oxfordshire, and we also serve the surrounding areas. So that's about 1% of the UK population. 4 hospitals, 3 in Oxford and 1 up 30 miles north of us in Banbury, with about 1,100 beds. And we have about 200,000 people come to the hospital to be admitted each year, or 200,000 admissions, and then that involves about 100,000 people. And for more than 20 years, we've got information on their demographics, the diagnosis codes, procedures, when they come to hospital, either as an outpatient or as an inpatient, and their various laboratory tests in microbiology and elsewhere, other blood tests that they've had. And then from 2016 onwards, when the hospital adopts an electronic patient record, we then have information on vital signs, imaging reports, prescribing, including antibiotics and other drugs. So really quite a rich data set to begin to analyze things. And before I move on, just a bit of a plug for the data set at the moment, at least. Provided you're a researcher who is part of the university or a researcher at any other organization that has an agreement with the university, then you can propose a project to do on this data and filling in a simple pro forma that then goes through a research committee that would then approve it. And for now, the data is free. It's sort of provided by the Biomedical Research Centre. So if you have questions you want to ask, then do chat to me afterwards and I can tell you more about that. So thinking about antimicrobial resistance, it's a global concern. Probably quite a few of you are here because you're interested in antibiotic resistance. But and there have been various attempts, and this is sort of one of the most recent ones, to quantify the burden of AMR. And you can see that actually AMR, there's no part of the world that isn't affected by AMR in the plot there on the left-hand side as you look at the slide. And actually, you know, Western Europe is, if I just pick it out there, if you can see the pointer there, it's you can't, but okay, I'll do it here. Yes, you can see Western Europe is here. So although it has some of the lower lower amount of burden globally still has a substantial burden. And the sorts of infections that cause problems are things like lower respiratory tract infection, pneumonia, and then also bloodstream infection as well. And these are some of the most common causes of death related to AMR. So if we now sort of zoom in a bit more and think about, well, it may be a problem globally. Is it a problem in Oxfordshire? And so one of the sort of initial ways that we've looked at this is to think about E. coli bloodstream infection. So E. coli bloodstream infection is the most common cause of bloodstream infection. And we have sort of several hundred cases of this a year. And so we're then able to ask some questions about, is resistance making a difference here? So it's typically associated with urinary tract infection or intra-abdominal infection, but it can have other sources, and it can obviously then go on to lead to severe infection and poor outcomes for people. And I've sort of given you a bit of a screenshot of our local antibiotic guide there. And what you can see is that our sort of first-line treatment for this is Kermoxiclav and a single dose of gentamicin, which is a second antibiotic. And this is all fine, but actually it turns out that our local resistance rates to Kermoxiclav are about 25%. And you might say, well, is it still okay to continue to recommend giving people Kermoxiclav when actually you have such high resistance? Now, our own belief had been that actually by giving this single dose of gentamicin, we could offset some of that resistance, buy ourselves a bit of time. But is this actually true? Or is actually our policy that you can see here causing harm? So before I sort of delve into answering that question, it's just worth saying, well, why don't we just target the treatment that we give directly to the bacteria that's causing the problem? And the answer is sort of twofold. One is that for where we can make a diagnosis, this actually takes time. And it takes between sort of 1 and 3 days, because it takes time for the samples that we've taken from patients to be incubated and to start to grow bacteria. And then we need to take them through a whole series of different steps to identify them and then work out what antibiotics will work for them. But actually, this is only in the minority of infections, because in most infections, we never actually identify the cause at all. So most of the time we give antibiotics, we're giving for a particular patient, we're giving them empirically, we're giving our best guess of what we think will work. But we also know, and this is the sort of well-cited paper from a number of years ago, that where patients have really severe infection, in this case septic shock, for every hour that you delay giving treatment, the percentage of them survive declines. And so we end up with this balance. We've got sort of potential harm from the current infection, and we also want to have the best possible chance of treating people, but then we're trying to balance that off against the future risk of antimicrobial resistance, both in that individual patient and then in the population as a whole. So because if we just simply prioritize treating every patient in front of us as effectively as possible, the trouble with that is that it may then drive, sort of accelerate the process of antibiotic resistance, makes things worse. So we come back to our particular question, and this is something that Chang, who some of you will have met, who was a PhD student working with me, looked at, was to think about patients admitted to our hospitals with a diagnosis of E. coli bloodstream infection who were treated with essentially what our guidelines would recommend, Kermoxiclav plus or minus some other antibiotics. And we looked within what we define as a sort of baseline period, 12 hours before to 24 hours after their blood culture was taken, and looked at 30-day all-cause mortality. And what we were considering was if people had active antibiotics, by which we meant the Kermoxiclav component, the bacteria that was grown was susceptible to that in the lab, versus if they had inactive Kermoxiclav, that isolate was resistant in the lab. And we adjusted for a whole series of covariates that we thought might be important in terms of predicting patient outcomes. And in the sort of first analysis that Chang did, actually applied a Cox regression model. I'll come back to some different approaches later. So we start out with just over 2,500 bloodstream infections of interest. Quite a few of them are discarded either because no antibiotics are recorded or because different antibiotics other than Kermoxiclav are given. And then we're left with 1,700 bloodstream infection episodes. And broadly speaking, your chance of having inactive antibiotics, i.e. Resistance to Kermoxiclav, it was more likely if you were more comorbid, you'd spend more time in hospital, and with hospital onset infection. There were some characteristics in terms of vital signs and blood tests that differed a little. For example, patients with inactive antibiotics tend to have lower albumin, again, a marker of potentially being more unwell, but actually not sort of huge differences across the board. Now, you remember I showed you that plot which suggested every hour matters. Well, now if we look at how long it took people to get back on the right antibiotics, actually, or on effective antibiotics, at least as far as the lab showed, the sort of median time to rescue was just over about 2 days. So this is time from having the blood culture taken to actually starting effective antibiotics. However, actually, there wasn't as big a difference as you might expect in the kind of observed mortality, at least, between those who received initially inactive antibiotics and those who received active antibiotics. However, this is clearly just the observed data, and we can do much better than this. So the first thing that we did was to look at the impact of co-amoxiclav activity, just simply judged by what, if you like, the sort of routine lab in the hospital would say was resistant versus susceptible. And adjusting for all the other markers of severity, you'll see that we don't really find any evidence that antimicrobial resistance is making a difference. You might say that's a bit surprising, and I think we were a little bit surprised by that. Of course, you then have to start to think, well, what does antibiotic resistance mean? How did we label things as resistant and susceptible? And the way that works is essentially we attempt to grow bacteria in the presence of an antibiotic. So here we've got a whole lawn of bacteria growing on an agar plate, and we've sort of zoomed in, and then we place this strip on the plate which releases varying amounts of antibiotic along it. So at this end, it releases a very small amount of antibiotic, and you can see the bacteria all growing in the background, and at this end, a lot of antibiotic, and you can see the zone of inhibition here. And we can sort of read off somewhere in the middle and see that actually a concentration of about 1 corresponds to the sort of minimum amount of antibiotic sufficient to stop growth. So then what we do is we say, okay, well, every particular bacteria has a minimum amount of antibiotic. Let's pick a number, and above this, we'll say that things are resistant. So for co-amoxiclav, it's actually 2 drugs, but for the kind of main component of it, that number is 8. So anything where that minimum amount of needed to inhibit growth is greater than 8, then we'll say it's resistant. But what if that actually isn't the best choice? Right. I'll come back to how we got to 8 in the first place as a number. So what we then did was to say, okay, well, if we look at different levels of antibiotic resistance that we can measure, so starting sort of here with the first thing that would be resistant, then needing double the amount of antibiotic compared to that, and then even more than that, what we began to see is that we had some evidence that where you had very high levels of resistance, actually in this categorical model, then you would begin to see that resistance was making a difference to 30-day mortality. And then if we just sort of focus in an updated model, just to consider high-level resistance, then you can see that there's, in this sort of exploratory analysis, that there's some evidence of increased mortality, and actually a hazard ratio approaching nearly 2 for having high-level resistance. And you might remember that I said actually 25% of people have resistance to co-amoxiclav, so actually there's potential for quite a few people being harmed. But we had this strategy that we gave people an extra dose of gentamicin because we hoped that that would sort of tie things over and protect them. Actually, it turns out that that doesn't really help, and this is slightly surprising. So although the gentamicin itself is active, actually when you add it in, this doesn't get rid of the effect of increased mortality from co-amoxiclav resistance. In fact, there's no statistical evidence that those two are any different. But if we give a different antibiotic which is active, like a different antibiotic, like say ceftriaxone or ertapenem or something else, then actually this effect is then we see basically the point estimate coming back down towards no effect. So what do we conclude here? Well, first, I mean, there's a simple lesson that high-level co-amoxiclav resistance appears to be increasing deaths from E. coli bloodstream infection in Oxfordshire. So even though we might think that we don't have much of a problem with AMR here, there is evidence that it's causing harm. And there's this clinical point for me and colleagues giving advice in the hospital that actually trying to buy time with this single-dose antibiotic, this gentamicin, this aminoglycoside, which provides about 1 day's worth of extra treatment, it really doesn't reverse this. And so I've had this sort of back and forth discussion with my colleagues about what our local guidelines should reflect. And the problem is it's moderately easy to quantify the harm from resistance, but it's much more difficult to quantify what will happen in future if we get accelerated resistance to other antibiotics. And so there's a lot of reluctance to change practice on a guideline level, but actually for individual patients where we're looking after sick patients, I think this has changed the way we deal with things in the hospital. But I think there's also a much more sort of generic point here, which actually is this gives us an insight into a better way to set antibiotic resistance breakpoints, because how we decide whether something's resistant or susceptible is largely driven by these sort of ecological patterns that we see. So we see, if we take a whole series of bacteria and we just look at what level of minimum inhibitory concentration stops them, or minimum amount of antibiotic to stop them growing, in the sort of wild type population, we see a bit of a spread, and then we sort of hope that we see a bimodal population, and then everything that's up here is resistant. But just because this happens, it doesn't mean to say that everything over here necessarily is associated with treatment failure. It's just that these are the two distributions that we see. And actually, in reality, it isn't always nearly as clean as this, and it may be that the orange distribution abuts the blue distribution or even begins to merge into it, and then it's very difficult to choose a clear point. Whereas here, what we're doing is exploring the kind of intrinsic variability in medical practice to actually understand, well, what level of resistance really matters. And actually, it turns out that probably what's called resistant should actually be set somewhat higher than what's called resistant at the moment. Now, there are sort of some issues with the analysis as presented, but I'm presenting to you the sort of published work, and that actually it's possible to do better than what we've done within a sort of causal inference framework. I've not presented it here, but actually we get very similar results using causal approaches, so using a marginal structural model to analyze this data. And that very similar answer probably reflects in fact, that actually the amount of randomness in people's practice from clinician to clinician is really quite great. But I can talk more about that at the end if people are interested. So broad take home from the first thing here is, if you like, in my title, this is the broader argument that for some instances we do need to give broader antibiotics. So maybe the next bit of the title somewhat gives this away, but it's kind of interesting that we're going to get a different answer here. So one of the other really common infections that we worry a lot about is community-acquired pneumonia. And in the UK and in most of Northern Europe, actually, most pneumonia is due to Streptococcus pneumoniae, and that's nearly always penicillin susceptible. And so actually, much of the pneumonia, sort of represented over in this wedge over here in the blue, can be quite happily treated with penicillin or sort of relatively narrow spectrum derivatives of that, like amoxicillin. In the middle, though, we have a whole bunch of different bacteria that can be variably resistant to amoxicillin. And so these include things like Staph aureus, Haemophilus influenzae, and Klebsiella pneumoniae. And they all have different ways in which they become resistant, but they're less common. But there's a concern that they might cause pneumonia that then might not be effectively treated by amoxicillin. And then there are a whole group of other infections which are perhaps even less common, which would get referred to as atypical infections, which aren't treated by either co-amoxiclav or amoxicillin. And the other thing that happens is by the time people come to hospital, many of them have had treatment from their GP already, so they may have had some amoxicillin. So we then have this debate amongst people in the hospital saying, you know, should we be giving the broader spectrum antibiotic, the co-amoxiclav, or should we be trying to give the narrower spectrum antibiotic, the amoxicillin? And if you look at guidelines, what they tend to do is sort of resolve this by trying to group pneumonia by severity. So we have national guidelines both from NICE and from the British Thoracic Society, which would say if you have mild pneumonia, then you just get amoxicillin, and if you have severe pneumonia, then you get co-amoxiclav and a macrolide antibiotic, which is designed to treat atypical infections. Whereas our guidelines locally don't actually use co-amoxiclav at all. We have recently moved to recommend amoxicillin for everybody, but adding in the doxycycline again to cover atypical infections. Now, there's a question about who's right, and I share an office with a colleague over at the John Radcliffe, and I have to say my anxiety has always been that by the time people get to hospital, actually, should we be using co-amoxiclav? Because I worry about, you know, have they got one of these infections that won't respond to amoxicillin? But my colleague is very much of the opinion that actually we should be using a lot more amoxicillin, that people are far too conservative. The good thing for us, perhaps less good for patients, I don't know, but it is that in reality, there's so much variation in practice that we can use the data to explore which treatments work best. And this is what Jane, who's a postdoc working with me, has been looking at, looking from January 2016 until September 2023, we picked out 16,000 people who'd had pneumonia as the main reason that they came to hospital. And we then looked again, sort of trying to define different groups by what antibiotics people received to start with, at those who received amoxicillin, roughly a third of people, those who received carmoxyclav, half, and then there were a handful who, 15%, who received both amoxicillin and carmoxyclav. And then others received additional antibiotics as well, whether it was a macrolide antibiotic or doxycycline, both of which would treat these atypical infections. And then 9% received additional gentamicin, which wouldn't necessarily treat a chest infection, but might have been given because there was some diagnostic uncertainty. Now, we can ask a very naive question, which is to say, well, what if you got which antibiotic, what was then your 30-day all-cause mortality? And if we simply do it looking at the observed data, then those who get carmoxyclav do a lot worse. 19% of them die compared to those who get amoxicillin, where just under 9% die, and those who receive both, where people were quite sure somewhere in the middle. But of course, this is clearly not very helpful because more unwell patients tend to get carmoxyclav and then do worse. So what can we do to address this? And so just to talk you through a different statistical approach to what we used in the first study, here we use sort of two relatively simple causal inference-based approaches to try and understand what's going on. And under some specific assumptions, which I've listed on the slide there, using either propensity score-based matching or using inverse probability treatment weighting, we can produce effect estimates from observational data that may approach those from clinical trials. I say may because it's obviously contingent on actually being able to meet the assumptions, which it's almost impossible to completely meet. But what we basically say is conditional on what we know or what we observe, then actually we can basically treat the carmoxyclav treated individuals as comparable to the amoxicillin treated patients, provided the other characteristics are well matched. And that then kind of is where the sort of parallel to the sort of randomization in the trial comes in. And with the matching based approach, we try and sort of model the propensity or the probability of being assigned to carmoxyclav or to amoxicillin and match people with similar scores to create a data set for analysis. And then whereas the weighting approach uses the sort of inverse of your probability of receiving carmoxyclav, for example, to balance patient characteristics across the amoxicillin and carmoxyclav treated groups. And there are sort of varying assumptions, but I think the main thing that I'm going to pull out for you is that actually clearly here you're making an assumption that for this really to work, that you need no unmeasured confounding. There's also sort of you want to make sure that you've achieved good balance between the groups by using either your matching or your weighting, and you also have to make sure that no sort of level of your covariance perfectly predicts either carmoxyclav or amoxicillin, which otherwise will cause a problem with the modelling. So when we do this, so we use baseline carmoxyclav versus amoxicillin as the sort of exposure of interest. We exclude the people who receive both. We look at 30-day all-cause mortality and then adjust for a number of things which I've listed on the slide there that you might expect. And the benefit of using this detailed electronic healthcare record data is that actually we can adjust for a number of things that people aren't necessarily normally able to adjust for because they just simply don't have that richness of data. So we can get, we hope, as good a control of confounding as we possibly can here, accounting for things like demographics, healthcare exposure, the actual severity of the illness when someone first comes to hospital, both by individual markers and then also using composite severity scores that are widely used in pneumonia. Now, the answer we get here is really quite surprising, that we actually find that, for me at least, maybe slightly disappointing because I wanted to say that carmoxyclav was necessary, but actually we find that there's no evidence that amoxicillin has different outcomes compared to carmoxyclav using either the propensity score matching approach or the inverse probability treatment weighting. And then a sort of more traditional multivariable logistic regression also gives you a similar answer of there being no real evidence for a difference. Of course, the observant view will notice that actually we can't exclude meaningful increases or decreases in mortality because even despite having had the data that we've got over a large hospital in a relatively long period of time, we still don't have as much power as we might like. The other thing that we've done here is just look at cases where we have complete data. If we go back to all the cases and use imputation to enable us to use all the data, then we again don't see an evidence of a difference, although perhaps the point estimates are somewhat higher, suggesting potentially some possible residual confounding rather than necessarily harm from Kermoxiclav use. The other thing that we can do is to ask the question, well, does adding antibiotics make any difference? And we find that adding macrolides or doxycycline, there's really no evidence of them impacting mortality at a population level. You might say, okay, well, that's fine. Maybe many of these cases were mild. What about the severe cases? Did it make any difference in those? And actually, when we stratify by severity score, again, we don't really see any evidence that amoxicillin is any different to Kermoxiclav across even in the severe pneumonia group. So this is sort of surprising, really, because I was worried about all these causes of pneumonia that we'd sort of learned about at medical school that amoxicillin might not treat. But at least at a population level, it turns out that maybe that isn't as important as it might be. So I think this challenges our sort of national guidelines and perhaps lends some support to our local guidelines in that we don't find that amoxicillin is really adding a great deal here. But it also challenges the fact that we frequently, you saw that in over half of patients they had some sort of additional antibiotic added, and there isn't maybe a great deal of evidence to support that. But there are some limitations. We've got these relatively broad confidence intervals. We obviously have unmeasured confounding still. We use diagnostic codes to identify pneumonia here, but you get similar results if you use radiology. Doesn't apply to ICU patients. And there's sort of, I think perhaps the biggest issue that will limit the kind of impact of these findings clinically is that actually we're sort of reporting what happens at a population level, whereas actually there may be people who are less common but who would benefit from different antibiotics, and their infections at the moment are quite difficult to pick out. And so I think there's clearly probably some work here in that this could well motivate trials, a trial or further trials evaluating optimal treatment for pneumonia. But it also points to there being a need for better diagnostics to pick out the people who may benefit from broader spectrum treatment. So those are my first two studies. More briefly now, thinking about the third, which is thinking about how we use antibiotics better. So when we think about how much antibiotic to give someone, we usually think about two things. The first is pharmacodynamics, which is essentially the way in which the antibiotics optimally kill bacteria. And some antibiotics work by killing bacteria when they have a very high peak concentration. Others work by consistently having a level which is above the sort of minimum level to kill the bacteria. So gentamicin, which we talked about, works by this concentration-dependent killing, whereas the antibiotics down here, like penicillins, tend to work by having a level that's consistently above the level required to kill the bacteria. And once we understand something about how the individual antibiotics work, we then need to understand how an individual patient tends to respond to being given an antibiotic. How does the antibiotic that's given get distributed, metabolized, and excreted? And so, for example, different patients, those who are critically unwell, may get rid of antibiotics faster and need more antibiotics, whereas some patients may actually excrete antibiotics more slowly and need less. And for many antibiotics, we can get away with actually using a single dose, or at least current practices. It may be that there are optimal, better ways of using antibiotics, but for some antibiotics, actually, the gap between what's sufficient to work and what's toxic is much smaller, and one of those is vancomycin. And so, due to a concern about underdosing in our hospital, we introduced a new guideline for how we should dose vancomycin in our hospital. And what this did was to target the sort of lowest level of antibiotic that we saw just before we gave the next dose. So that's the trough level of, and we wanted this particular target on the slide there of 15 to 20. And the way we achieved this was to think about how much people weighed and also what their renal function was like, to recommend what initial dose people got and what they got for the first couple of days of treatment after that. And what we aimed to do then was to use the data that we'd routinely collected and this is where the Xing is, who's sitting at the front there. And we had data from just under 4,000 people who'd received vancomycin treatment for more than 24 hours. The first thing we did was to check, were people actually following the guideline? And actually, it turns out broadly they were. So around 70 to 80% of the time, they followed the initial recommended loading and maintenance doses. Kind of just as an aside, it's sort of interesting that different places did different things. So there appeared to be greater compliance in those with older age and worse renal function, but that might be partly because actually the sort of historic doses that were given tended to be lower and closer to the doses recommended in those groups. So it may just be that actually people were just sort of tending to follow previous practice. But then actually compliance was also lower when some specialties looked after you. So if you were looked after by trauma and orthopedics and cardiology, you were less likely to get treatment in line with the guidelines than if you were looked after by the medical team. And then when new junior doctors started each August, we saw sort of prescribing somewhat deteriorate. And then actually, as you went until the following July, you then saw an improvement. Small, but the effect was there. And not only were the right doses given most of the time initially, but actually people made sensible adjustments when they got information back. So where the levels given were under target, then what tended to happen, if you see on the panel on the left-hand side here, you can see that most of the time actually your chance of your dose was being increased was relatively high. Whereas if you were over target, then you tended to get your dose reduced. There was some account made for renal function here, so you were less likely to have your dose increased if you had poor renal function, and similarly, if you had very good renal function, less likely to have your dose reduced if you had poor renal function, increased if you had poor renal function, and less likely to have it reduced if you had very good renal function. We then looked at, well, what happened to people over time? How likely were they to ever reach target levels? And actually, it turned out that your chance by 5 days of reaching the target levels was only just over half. So this is everybody on the left-hand side in panel A, and on panel B, this is sort of contingent on still being on treatment. And so you can see that actually the initial loading dose that you got didn't really make a great difference to whether you ended up on the right treatment. And so this really then made us think, well, actually, did we get it right with the new guideline that we wrote? Actually, or were we failing to dose people appropriately? And so what we were able to do is use the models here to actually come up with a recommendation about how to improve the dosing of vancomycin. So we could see that drug levels were independently higher in older patients than those with worse renal function, which probably meant that actually we needed to give more antibiotics to younger patients. So previously, the guideline just looked at weight and it looked at renal function. It didn't consider age. So what we did was to propose an update to the guideline that basically said in younger patients, give a lot more antibiotics. So you can see in the dotted lines for each level of renal function and for a particular weight, what was recommended, and then the model estimate in the solid line, and then the sort of new recommended dosing in the dashed line. And actually, the concern about giving too much vancomycin is renal toxicity, but we saw that with existing practice, the instance of acute kidney injury was low, and most of it was mild. So the details here don't matter so much about vancomycin, but I think that the point here is that actually we could use this routinely collected data to say something about actually how to dose antibiotics more effectively. However, before you think this is a sort of amazing thing that could be used much more widely, the issue is that we don't measure antibiotic levels for many patients. And so we're somewhat limited in how we can apply this. But for those who are interested, I think it is worth thinking more about using sort of more informed use of antibiotics. And there are certainly kind of research groups and organizations like TDMX that are interested in providing sort of ways of trying to calculate dosing more appropriately. And so if any of you are working clinically, it may be worth having a look at that as well as following your local guidelines. So next question is, well, how do I know that my patient's recovery is expected? are antibiotics working? So this is something I get asked. We go around and we give advice to people that within the hospital, whether it's in the intensive care unit or in particular wards, and they say, well, you recommended giving this particular antibiotic. How do I know it's working? When will I know it's working? And people have very different responses to infection, but what would be quite nice is to have some unified way of saying, are antibiotics working? And one sort of area where people have thought about this a little, quite a bit, is thinking about actually monitoring how children are growing. And there's this concept that if a child starts at a particular weight, that they should then continue to grow along a particular line, that there's sort of centile lines, so that you know that the child is growing as expected. If it starts off on the 25th centile, then a month later, you might expect it to be roughly on the 25th centile too. If it falls off that and is much lower than expected at the next time point, then actually that may be a cause for concern. So could you have the same thing whereby now what we're looking for is sort of recovery in inflammatory markers? So instead of looking for growth, we're looking in sort of things going down. But so instead of sort of dropping off your line, we'd be like looking for people going up a line, going up centiles to show that they're not recovering as expected. There isn't really anything like this in use at the moment. So lab tests are widely measured. We measure sort of white cell counts and CRPs, which sort of measures of inflammation and infection. But actually, the kind of interpretation of those is really quite sort of quite ad hoc and sort of lacking really any systematic approaches. For procalcitonin, there's maybe some greater sort of systematic sort of use of that, but that's largely been because it's been used in specific trials and people have used specific thresholds there. So for example, CRP, which is often measured, we probably spend hundreds of thousands of pounds measuring each year in the NHS, if not millions of pounds. We know that if we measure it 4 to 5 days later, if it's still high, it's associated with a worse outcome, but that's not really very helpful if you are trying to make a decision about what to do today, tomorrow, the next day, when someone's first admitted into hospital. There are then scoring systems that are used in intensive care settings, like the SOFA score, but there isn't really a systematic use of these inflammatory markers. So what we did in this study was to think about, okay, well, if we take these and we follow patients coming into hospital with suspected bloodstream infection, can we say something about how their vital signs and how their lab tests change over the time they're in hospital? And the first thing we do is to fit a mixed linear model to basically account. We want to know what the overall pattern looks like. We want to know what the impact of different covariates like age and sex and the pathogen infecting you and various other things is. And so we can look at those as both fixed effects in the model, but also look for interactions with time. So do they change how high your inflammatory markers go, and then do they change the sort of pattern of how things recover over time? And that lets us learn something about what things look like on average, while allowing for individual variability between patients and bloodstream infection episodes. The other thing that we can do is just to try and group the different responses that we see into different subgroups or different latent classes. And here we pick a number of classes, or we may choose a number of classes based on varying approaches, but we say, okay, well, we're going to look at 5, for example, different classes and see what these look like. And then there'll be some that follow maybe what we think is sort of a normal recovery, and there'll be others that maybe look different. And then if we take the normal responses, can we then use the same methods that we use to come up with those pediatric growth charts to develop centile reference charts for recovery of inflammatory? So roughly a quarter of all people who come to hospital end up having a blood culture taken at some point, many more in emergency admissions than those who come for a planned admission. And so we had just under 90,000 suspected bloodstream infection episodes to look at. About sort of 8% of those are positive, the culture positive for a pathogen, either a gram-positive pathogen like Strep pneumoniae or Staph aureus, or a gram-negative pathogen like E. coli, and then some are a mixture of multiple pathogens together or rarer pathogens. Around 5% of the blood cultures get contaminated with the bacteria that are sat on people's skin, and then the rest, the large majority, are cultured. Most of these blood cultures are taken when people come into hospital, and they're mostly associated with respiratory or urinary infections or multiple combinations of infections. And one of the sort of novel things that we find here is that actually the response that you see in your inflammatory markers depends on the sort of pathogen you're infected with. So if you're infected with Streptococcus pneumoniae, which is a common cause of pneumonia, then you tend to get a much higher CRP response, whereas, and also for beta hemolytic streptococci, so things like group A strep that you may have heard about, they tend to generate these much greater responses, whereas for some other things, you see much flatter responses. You see more prolonged responses over here with a fungal infection, so Candida, or a polymicrobial infection, so multiple bacteria growing together. And then in those who are culture negative, we see much flatter responses. This is a mean response, so it's probably a combination of people with a higher response and then many lower responses as well. So the pathogen that you get infected with determines how your one particular measure responds, and the same is true across other measures as well. Similarly, where your infection is matters too. So if you have an infection within the abdomen, so you have appendicitis, or you have a perforation of your bowel or some other problem like that, then you tend to get higher responses. Whereas if you've got an infection around your head, in the central nervous system, then actually you get much lower responses. And this is even after adjusting for the pathogens causing the problem. So responses, who's infected matters, what's causing the infection matters, and where the infection is matters. So all of these things contribute to determining what happens to your inflammatory markers. When we try and divide these different things up into these different latent classes, you see that most people follow this pattern in the red that you can see, where you get a rise that peaks on day 1 after the blood culture is taken and then gradually declines over the next 3 to 5 days. There's a second group where that rise is somewhat later, and you tend to peak on day 2, but you recover in a similar way. And those two we regard as, if you like, the sort of expected response, and they account for just over half of infections. We then have people who recover more slowly, those who have a late peak, and then those who don't really have much response at all. They have a sort of very flat response. And we can look at how likely people are to belong to one of the 5 classes, and if it was completely random, then these would all be sort of 0.2. So you can see that there's pretty good evidence for people fitting into the 5 different classes that we see. The people who tend to respond more slowly or to have a delayed peak in their inflammatory markers are older, more likely to be male, they're more comorbid, they're more likely to have a hospital-acquired infection, and more likely to be immunosuppressed. Whereas those with a lower response tend to be younger and more likely to have community onset infection as well. Does this matter? Well, if we look at 30-day all-cause mortality, comparing to those who peak on day 1, those who recover more slowly or have a delayed peak have an almost 2 times greater chance of dying, whereas those who have a low response are somewhat less likely to die with an odds ratio of 0.76. And there's no evidence of a difference between peaking on day 1 or day 2. Probably just skip over the detail at the bottom, but essentially you see somewhat different patterns by pathogens. And so what we do is combine day 1 and day 2 to sort of identify the peaks on day 1 and day 2 to identify who we think are typical response, and to come up with a chart that looks a bit like this. So here you can see that if you come in as a sort of typical patient, you would see your CRP come in just over 100 at admission to hospital. It might rise on day 1 and then decline afterwards. And actually, if we make this chart for different infections or for different pathogens, it looks remarkably similar. And so what we can do is we can actually present a single chart that allows us to sort of cope with all that different variation that I showed you to start with, because you just start at different points in the chart. Once you start at a different point in the chart, your recovery pattern is very similar. Making the point over here in this sort of panel B that you can't just say, okay, well, someone's CRP's fallen by 50 or it's fallen by 20%. The actual change in your CRP that you expect to see depends very much on where your CRP started in the first place. So if we look at comparing where you are on day 3 to your baseline, it matters hugely whether you started at 100, 200 or 300. Which is why perhaps people don't necessarily have intuitive rules, because they look at this data all the time, but actually there's enough complexity in it that they can't pick that apart. And most patients actually follow a centile, so this is useful. So if you compare day 1 to day 2, day 2 to day 3, and so on, you see that most patients follow their line within plus or minus 15%. There are a handful, though, where the centiles go up, and these are people where we would consider intervening. So in terms of sort of CRP response, this is potentially quite a useful approach for tracking whether people are responding as expected and for working out who we should sort of change treatment in or look for other causes of infection. There is a limitation that CRP is not measured at random, and so actually it's more likely to be measured when people aren't recovering as expected. So actually probably true CRP recovery may be more rapid. And then I think we'd like to take this work forward by tracking multiple parameters simultaneously to try, particularly those that change more rapidly, maybe over hours, to try and see where treatment's working. I want to leave you a bit of time for questions. I can see that the clock on the wall is strategically set for speakers to be 5 minutes fast, so it makes us not take too much of your time. But I'll probably spend 5 minutes or so just talking about this last project where we look at predicting discharge. And I think many of you will be familiar with the fact that in the UK, but globally, there's substantial pressure on hospitals, and there's a real incentive to try and get people home quicker, because that will free up capacity in the hospital, but it actually also might improve people's experience, because they might not spend ages waiting around in hospital for something once they're well. And how might it speed things up? Well, there's the logistics of getting home, booking the transport to take you, arranging with the family to get you home, preparing the things you need to go home with, and then also sort of preemptively booking the cleaning of the space and getting it ready for the next person. Also, if you can accurately predict how much demand you're going to have tomorrow or the next day or the next day, you can then plan activity. You can decide how many staff you need, whether you need to cancel planned admissions or whether you can bring in more people than you thought you could before. And actually, infection drives a lot of this fluctuation in demand, because with seasonal infection, pressure on hospital gets worse, as you're sort of familiar with the concept of winter pressure. So what we do here is to use a sort of fairly classical machine learning based approach. So we aim to predict hospital discharge within the next 24 hours. So we can do that at 8 o'clock in the morning or 12 o'clock at lunchtime or whatever else we pick. We look at all hospital inpatients, excluding maternity, because they use a different electronic record system, or will do shortly. Currently, they mostly use paper. And we then, through sort of expert consensus, we sort of pull together hundreds of potentially informative data points from the electronic records, and also try and think about what representations of those might be most informative. And then we train a sort of fairly standard XGBoost model, which actually for this kind of structured data tends to perform as well as some of the more sophisticated machine learning architectures a lot of the time. I'm not saying it's perfect, we're trying to do better, but it certainly does quite well. And we can, just sort of following this flow chart here, we sort of take our initial data and process it into the features that we want. We split it to have 2 years worth of training data and then a year's worth of test data, stopping just before COVID in this example. And we use most of the data that's available for training to train the model. We optimize the hyperparameters using cross-validation. And we then, when we get the data out at the end, we use a bit of the training data that we've held back to calibrate it so that we know that we're getting actual probabilities out of the model, and then we can predict at an individual level when someone's going to go home, and then we can add up all those probabilities to come up with a total chance of someone, the total number of people are expected to go home. And the intuition here is relatively simple, that we're just exploiting patterns in the data. So here's an example where the longer you've been in hospital, the less chance you have of going home the next day, which probably is fairly intuitive. And in fact, it matters as well whether you came into hospital as a planned admission, and then you're more likely to go home after a sort of moderate length of stay in blue if you came in as an emergency. Similarly, the day of the week that we're making the prediction matters as well. So if we make a prediction in the morning, then you're less likely to go home within the next 24 hours on a Saturday or a Sunday or a public holiday, which may not necessarily surprise you, but I guess provides an opportunity to improve discharge efficiency. So how do we do? If you look at the kind of, it depends on what metric you like to look at, but if you look at the kind of area under the curve, the receiver operating curve that we achieve here, these sort of numbers are probably at the top end of what's described in the literature. They're not hugely better than the best examples, but they're better than many of them. And what this means in a typical population in hospital, we can end up being able to say, with about 50% certainty in terms of positive predictive value, when we say you're going to go home tomorrow, you will. And then when we say you're not going to go home tomorrow, we can be just over 90% confident that that's the case. When we bring all this together, if you look at the actual discharge in red and the predictions in blue, you can see that we're able to get fairly good predictions of when people are going to go home, or the numbers that are going to go home. Actually, there's sort of a relatively naive model that just considers a handful of features and uses logistic regression. Still does pretty well at this task, probably because actually their own, what we gain in the previous example is more precision at an individual level, but actually the prediction of the population level is somewhat easier. We're interested in whether we get it right for everyone or whether there's sort of better performance in some groups than others. We do somewhat worse for older people, and that partly reflects the fact that actually what determines that they go home is much more outside the control of what's in the hospital and also what's written in the medical record. We see performance improve somewhat if you have more training data. So kind of here, if you only have 1 to 6 months data, you do worse than if you have 12 months of data. But once you have about 12 months of data in a hospital, that seems to be enough. And then if you have older data, so if we use the same test data of 12 months, but we then use 12 months of training data, but sort of make it go further back in time, then we can see that performance declines a little bit. It's subtle, but there is a slight decline in performance as the training data becomes older. And actually, if we apply this now using data from this week, actually the performance for elective patients is pretty much preserved, whereas for emergency patients post-COVID, what seems to be happening in predicting their discharge has changed somewhat. And this sort of makes a point about if these models are going to be useful, they need to be updatable. What's important in determining whether people go home? Well, you might think it's all about people's vital signs. You possibly can't read all this at the back, but actually it's a sort of mixture of things. So what blood tests are they having? What procedures are they having? What treatments they're having? All of these things go into determining whether people go home. And you get a different list in elective admissions to emergency admissions. So it's possible to predict with discharge with sufficient accuracy that this actually might be operationally useful. And this outperforms most earlier attempts at this, and that's probably because of careful feature choice and feature engineering. We'd like to extend this to predict length of stay, also to predict multiple things at once, whether people leave the hospital having died or alive, and also discharge at different intervals. And it's sort of part of a much wider series of projects using machine learning to inform healthcare delivery, which I haven't talked about today, but again, I'm happy to talk to people afterwards if you're interested. So a sort of final slide here. I think bringing it all together, this routinely collected data can be useful to answer specific clinical questions, but I think also it offers actually quite sort of exciting opportunities much more generally, because we can exploit the sort of intrinsic variability in practice together with causal methods and the scale of the data. And we can then use that to generate hypotheses. We can use it where trials aren't necessarily feasible. We can use it in the case of infection to think about actually, well, what is antibiotic resistance? Can we dose antibiotics better? And then I think you've heard an awful lot about machine learning being useful, but I think operational delivery of healthcare is another area where you see it being used more and more. So a few thank yous, particularly to Chang, Tilu, and Jane, whose work I presented, David Clifton, who contributed to the last piece of work, and Sarah Walker, who I've worked closely on this, a few of the students who've contributed at the top, and then the sort of modernising medical microbiology group that I work with quite closely on this as well at the bottom. And then finally to thank the people who keep the database going and the people of Oxfordshire who contribute to it. So thank you very much.